Cars, applause, laugh.
Okay, I believe we are
Run the
ready to go.
show.
We're good to go.
All right. Hey, thanks for coming out today for the seminar. It's my pleasure to get to introduce Nikaan Koupaei Abyazani. A funny story, I think the first time we could have a gathering again at my lab, we met outside of the park, and Nikaan showed up and the rest of the lab, and I think half the lab were shocked because they had only ever seen Nikaan in 2D. Nikaan is one of our pandemic starters, and so it's been a real pleasure, but has all been added since then and doing great work, and it's been fun to kind of start a student completely remotely and then to really kind of, once we were back in the building, to kind of move forward on the work. But during those couple years, Nikaan has worked quite a bit on this project we'll hear about today on trying to understand this idea of carbon cycle variability and why that matters and why that's relevant right now, as a lot of people are thinking about carbon sequestration and mitigation through ecosystem carbon management. By way of introduction, Nikaan did join my lab. He asked a couple years ago, he was finishing up his physics degree here at UW-Madison. He has a double major in physics and astronomy and a certificate in math, which is a good combo. But wanted to, actually do some science that means something to this, planet that we live on, and wanted to come over and do graduate work in atmospheric oceanic sciences. Reached out to me, and I didn't have quite a project ready to go with him at the time, but I mentioned that I have decades of data that really need to be looked at by somebody. And so we kind of scraped together an idea and some funding through a mix of things, and we're able to get him going. During his time at UW, both as an undergraduate, where he was a physics peer mentor, and then here in our department, as well as in the physics department, serving as a teaching assistant in physics and in global change. And he had also done some undergraduate research on hydrogen emissions in Earth's upper atmosphere, so completely different part of the universe, but still good stuff. And today we'll be hearing about the work that is leading to his master's thesis on the influence of interannual carbon variability on long-term sequestration in proximate northern forests and wetlands. So I think I'll leave it at that and turn it over to you. Thanks.
Thank you so much for that introduction, Amber. Can everybody hear me all right? Good? Okay, cool. Yeah, so today I'm going to be talking about atmospheric actions and the carbon cycle. Hopefully those of you who are maybe not familiar with this area of research can kind of learn something new. So here's kind of an outline of how we're going to go throughout the talk. So I'm going to provide some background information on the carbon cycle, ecosystem types, interannual variability, climate change, and then something called natural climate solutions, which I'll kind of define. Then we'll kind of dive into the study itself, where I'll name the study sites, the stream flow gauges, how we measure these fluxes through Eddy covariance, and then go through some results, and then provide a discussion of those results. So first thing I want to address about the carbon cycle is carbon significance. So it's fundamental for the existence of life, right? And it's a dominant global means for energy production, right? So what you're seeing here is a picture of a coal mine in Indonesia. And you can kind of see how big of a reliance that humans have on these fossil fuels. And the burning of these fossil fuels have kind of triggered a lot of these researchers to come up with different ways of carbon mitigation strategies. One of which I will get into, which is natural climate solutions, and I'll kind of define that later in this talk. So the carbon cycle also has lots of reservoirs. You can see here, this is the percent of the Earth system's carbon, and then the reservoir that it resides in. You can see that the deep water in the ocean holds a bunch of carbon, right? However, the carbon that comes out and into the fluxing in and out of that carbon is insignificant on human timescales because it takes a long time. So this is kind of a long-term flux that happens within the deep water of the ocean. What we're going to be talking about today is the vegetation and soil carbon fluxes, mostly. They comprise about 6% of the Earth system carbon. but they play a large role in carbon fluxes, right, because they have a very, very fast flux on very, very small time scales. So that's what makes them really significant. So here is an image that Srinath Pillai shared with me, one of the PhD students in the lab. And it basically shows different types of ecosystems. And the type of ecosystem, different types of ecosystems, and then the region that they reside in. It's showing kind of that partitioning between above ground and below ground carbon at these ecosystems. So you can see the wetlands here have lots of carbon stored in their below ground carbon, such as the soil, whereas something like a tropical forest will have an approximately equal partitioning between above ground and below ground carbon. So it goes to show that the carbon reservoir differs between above ground and below ground depending on where the ecosystem is located and also what type of ecosystem you're looking at. So of course, I've been talking about carbon fluxes, right? These carbon reservoirs don't, the carbon in the reservoir doesn't stay there, right? You have carbon fluxes, you have that land to atmosphere carbon flux, which is, can be due to anything from land cover change, anthropogenic activity, and then you have the atmosphere to land flux, which is better known as photosynthesis, that carbon uptake. In addition to this vertical carbon flux, there's also a lateral carbon flux, which is basically this inter-ecosystem carbon flux that is goes through, basically it's transported through stream flow or any really flowing body of water. And I'll kind of get into more of that later in the talk. It's actually included in the study as well. Just to briefly go over the Eddy covariance method, I'll kind of show you a real flux tower later, but just a brief introduction that what Eddy covariance does is, in a nutshell, is just measure these carbon fluxes, these CO2 and methane fluxes. And above the vegetation here, you can see that you kind of place this flux tower within the ecosystem. You have all of this carbon respiring and being taken up by the vegetation. And these eddies, due to the day and night cycle, kind of transport that carbon up and down within these kind of circular motions. And then the wind eventually takes them through the flux tower, and then a flux calculation can then be made afterwards. So there's a lot of math and theory that goes into this, but I'll kind of leave that there for now. And I'll show you kind of the different instruments as well that are kind of equipped on these flux towers. So the carbon that we're looking at, the carbon fluxes in particular, are driven by a lot of variables, right? Anything from temperature and then water and energy play a large role, and we'll see this kind of in the study. Water in terms of precipitation and discharge. Of course, you have energy kind of accumulating or energy causing photosynthetic uptake to occur. And then you have sensible and latent heating as well. The latent heating term kind of shows the amount of linkage between the water and energy budgets. So that's also an important term as well. This basically will be further, so I'm going to talk about this in the study and how exactly these flux magnitudes are impacted by these drivers. So I'll learn that soon. So just to familiarize y'all with some ecosystems. The ones that we are going to consider in the study, one of them are forests. I think everyone knows what a forest is. At least, so I'm not going to tell you what a forest is, but some tidbits about this are that they're responsible for about 90% of the carbon exchanges between the land and the atmosphere. So if you did not have these ecosystems, you could imagine that there's not much of a land-atmosphere carbon flux between those two reservoirs. Second, the dominant carbon storage location depends on the region. So for example, if you have a boreal site, maybe like a Canadian forest, you would tend to have more carbon accumulated in the above ground, or excuse me, in the soil, so below ground. And then something like a Midwestern US forest may have more carbon, or tends to have more carbon stored within its vegetation and above ground. And then lastly, of course, we have a lot of deforestation and degradation that causes these ecosystems to become large carbon sources, right? Especially in the tropical regions where you have these developing countries trying to grow their economies. And they use these rainforests and forests, like tropical forests, for their resources, right? And that is a huge problem right now. Even though deforestation has kind of decreased overall, there is still a significant problem in that region in terms of deforestation. So, and it has also been kind of estimated that these activities contribute to about 1/5 of the global greenhouse gas emissions. So the next ecosystem type that I want to get into are wetlands. So wetlands are kind of characterized by their waterlogged conditions, either seasonally or permanently. And they encompass a bunch of ecosystem types that you may have heard of, such as bogs, marshes, fens, swamps, things like that. They can all be kind of put under the term wetland. And then what makes these ecosystems particularly interesting is that their greenhouse gas fluxes are highly dependent on the water table depth. So for example, if you have a water table that is below the soil, then you tend to have lots of decomposition occurring, and you have the ecosystem become a carbon source, and then a methane sink, typically. And then if you have a water table that's above the soil, so you have that soil being saturated, typically you have methanogenesis that occurs due to the microbes in the water, and you have that surface outflux of methane. And then that wetland becomes a methane source. So this is like kind of a large area of research for things like rice paddies and rice agriculture. So now I'll get into interannual variability, or IAV, from here on. I'm going to define 3 different terms. So this is where kind of the math comes in. The math is not really hard, but I'll kind of define these terms. So we have this GPP term, which is basically the amount of CO2 that's accumulated through photosynthesis. You can think of GPP as gross primary productivity, which is the carbon uptake term. And then conversely, you have RECO, which is your ecosystem respiration term. And this is basically the carbon source term. So how much is this ecosystem respiring carbon? Then you have NEE, and that's on the top right there, that kind of links these two, puts a relationship between these two. So you have NEE equaling the difference between RECO and GPP. So NEE is net ecosystem exchange, and it quantifies the carbon source or sink status of a particular ecosystem. So for example, if you have a carbon source, then you're going to have positive NEE, and that carbon sink would be negative NEE. So you kind of think of it like that. And interannual variability is a hot topic because this is just me putting random arrows. This basically shows that across the year, many ecosystems see high interannual variability. So sometimes you see carbon sources, sometimes carbon sinks from year to year, sometimes even carbon neutral, where you have these two terms neutralizing each other, right? And the huge question is, how can we learn from this to develop models and eventually project that for the future, right? So if we can tackle this and completely understand the interannual variability, then it'll result in the decrease of uncertainty in models too. So there have been a lot of studies too on interannual variability, such as temperate forests by Schachter et al. And Grainer et al. Also ecosystem type intercomparisons by Novik et al. And then there have also been ones done in boreal forest as well. And what makes this particular study that I'll get into kind of unique is that we're looking at multi-decadal scales, so this is very much a long-term study. And then we're looking at clustered sites, so sites that are relatively close to one another, right? And also incorporated a natural climate solution analysis, and I'll get into what natural climate solution is a little bit later in the talk. So actually pretty soon. So all of this is happening in the backdrop of climate change, right? So just a reminder that we've been increasing our atmospheric CO2 concentrations, and current estimates have us at about 420 parts per million of atmospheric CO2 concentration. And the IPCC AR6 report, Working Group 1 that came out, I think it was last August, had this very buzzworthy statement where they mentioned that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. So I just put this up just to mention that they have the word biosphere here, right? And of course, unsurprisingly, climate change has a lot of effects on ecosystems. Anything from CO2 fertilization effects, where you have a lot of GPP all of a sudden, and then stuff such as carbon sources, where you have larger temperatures causing much more respiration. So yeah, climate change, research on ecosystems, or the relationship of climate change and ecosystem. Carbon fluxes are a hot area of research as well. So just to cap off the overview section here, so I'm going to define something called natural climate solutions, or NCS. And for those of you who aren't familiar, natural climate solutions are basically, they're a climate change mitigation strategy that takes advantage of the ecosystem carbon sequestration potential and kind of has these ecosystems suck out carbon from the atmosphere for a long time period. So there have been a lot of projections that have looked at how NCS can cause, or have projected how NCS can mitigate this carbon on long time scales. For example, this study in PNA, published in PNAS by Griscon et al., I believe, mentions that if we were to kind of neutralize our industrial carbon emissions at some point, then we should be able to mitigate about 37% of CO2 equivalent between now and 2030. And as you can see, this kind of, if we take this seriously, it has us become carbon neutral by about 2050-ish. But this is very optimistic, right? And it goes to show that NCS mitigation practices must be complemented by those industrial CO2 mitigation strategies, and therefore, it cannot be implemented by itself. So we do need those, must be complemented by other mitigation strategies as well. And so the way we approach biomes in the context of natural climate solutions is also kind of what this study is trying to look at. Do we treat different ecosystems in the same way, or do we treat them differently in terms of restoration efforts in order to sustain that carbon for a long time period for climate change mitigation? So this kind of caps off the overview section, and now I'll kind of go over the study itself here. So what you're looking at here is one of the study sites. This is a wetland in northern Wisconsin. Its name is Lost Creek. And I want to go over now the layout of the research and kind of familiarize y'all with the research questions that I tackled here. So this study incorporated 8 sites spread across these 8 sites. If you sum them all together, they provided 80+ years of carbon flux and micrometeorological data at half-hourly scale. And then what we wanted to kind of ask is, how does the NEE interannual variability of the forest sites compare to that of the wetland sites? And is this more a function of GPP, or is it more of a function of RECO? So more a function of carbon uptake or carbon respiration. Next, are there any significant differences in carbon drivers between or within biome types? And is this different on different time scales? So do we see differences of the dependency of these carbon fluxes on drivers on something like half-hourly scales versus long time scales like seasonal and yearly scales? And then lastly, as I've mentioned before, how we kind of use this information and apply it to NCS mitigation efforts is also something we consider too. So that's another question. The main hypothesis was the following. So we had basically, given any region, ecosystems will have the same interannual variability because we are talking about these clustered regions. Therefore, we would expect them to have a similar interannual variability. So just to show you some sites at a glance, and this is all citations, don't worry about that. So here we have wetlands right here, and then forests, and you can see that each of these have temperate and boreal, they're within temperate and boreal regions. So just to give a sense of where these are located, I'll kind of show a map here. So you have the northern Wisconsin sites and the Michigan Upper Peninsula sites right here. Those are the temperate sites. You can see how clustered they are. And then you have two of the Canadian sites right here, is a peatland and the deciduous broadleaf forest. Then the top left right there are your bog and then the evergreen needleleaf forest that are within the same basin, so that's why they're kind of overlapped by one flood time. So like I mentioned before, we also incorporated stream gauges, right? Remember that I mentioned that we have vertical fluxes and also lateral fluxes, right? And this has been motivated by work by people such as Buffin et al., which show that even though the vertical and lateral carbon fluxes don't have similar magnitudes, the lateral carbon fluxes are significant enough to contribute to the wholer kind of carbon budget. And therefore, to create kind of a full carbon budget, you need to incorporate these lateral fluxes as well. So this is what a stream gauge kind of looks like. It's basically measuring the amount of stream flow, kind of the amount of volume per unit time. The data is kind of reported in feet cubed per second. Data was acquired from USGS. And I'll just kind of go over the schematic just to show how lateral carbon fluxes work. So we have the carbon dioxide being uptaken by the vegetation. And this carbon kind of makes its way through the soil, into the soil. And if the ecosystem has a kind of a large water dependence, then it's going to kind of be flushed away in the form of, the carbon's going to be flushed away in the form of DIC, DOC, POC, and also PIC. And this is dissolved inorganic carbon, dissolved organic carbon, particulate organic carbon, and then particulate inorganic carbon. So that's kind of a simplified version of how this inter-ecosystem carbon flux works. Unfortunately, though, we were very limited in what stream flow gauges we could use. And basically, the only stream flow gauges that were kind of in a similar location to these sites were the Ottaquash Creek, the Lost Creek, and then the Sylvania Wilderness site. So that's the temperate, two temperate wetlands, and then the temperate mixed forest. So those are kind of the ones we considered with lateral carbon fluxes, but we did not have any for Willow Creek or any of the Canadian sites, unfortunately. Okay, so now I'm going to go into kind of the Eddy covariance method. I won't go into too much detail, but just to show you kind of what one looks like in real life. So this is the Eddy covariance flux tower in Lost Creek, and it's equipped with a bunch of instruments. So I'll just go over kind of three of them here. It has a lot more. You have the sonic anemometer. This is responsible for taking wind measurements, 3D wind velocities, and this facilitates the flux calculation. They have the methane analyzer, and also the carbon flux, or excuse me, the carbon dioxide and water vapor analyzer as well. So this is basically showing kind of the way that the flux is measured, and this makes the carbon flux measurements. If you have any questions on this, I'll try to answer them to the best of my ability after the talk. But yeah, I'll just leave it at that for now, so we can kind of look at the results now. So, okay, so what I'm about to show you here is the NEE spread. So remember, net ecosystem exchange spread of each of these ecosystems. Some of them I didn't include because they had small amounts of years of data. But so I'm going to show you the temperate sites. There are going to be a bunch of bubbles here, well, 3 bubbles that are showing numbers. These numbers are in grams of carbon per meter squared per year, and they basically show the standard deviation of the carbon uptaken by the ecosystem from year to year. So you have one number of carbon uptake for each year, and then taking the standard deviation is basically how I got these numbers here. So here are the numbers here. So Lost Creek, Sylvania, and Willow Creek, these are the temperate sites. And then the wetlands right here, and then the forests are over there. And what you notice is that there is a much larger spread at the forest site NE relative to the wetland site NE, right? So you're seeing a lot more variability from year to year at the forest sites relative to the wetland site. This is for the temperate region. And if we divide by the mean of that kind of cohort of fluxes, we can quantify the coefficient of variation. This is expressed as a percentage, and it basically shows you the dispersion around the mean. So how far away the standard deviation is from the mean. So N is basically representing the number of years of data available for that particular site. And yeah, you can see that Sylvania, right here, this is the mixed forest, has a larger coefficient of variation relative to Willow Creek and Lost Creek right here. And I think that mainly may be due to Sylvania being kind of an older site, an old growth forest. And I think these are relatively younger. You can also apply this to the boreal sites as well. So looking at now the boreal sites, and I'll signify what these are. So you have the wetlands and the forest. You can see again, relatively, the same story is kind of being told, right? Where you have larger variability at the forest sites relative to the wetland sites. And if we do this coefficient of variation analysis again, you can see that it's actually flipped now, that we have the forest site showing less dispersion around the mean, its own mean relative to the wetland sites. But of course, if you look at the N values, the number of years, then you'll see that there is not much, there's a lot more data at the forest site relative to the wetland sites here, to the boreal region. So have to take caution with that, and we can't really make any conclusive remarks until we get more data. So, there's a better way of kind of representing this, and that's looking at the time series of this. So here you can see that we have the date of the year on the x-axis, the NEE, which is recalling that NEE is the carbon source or sink status, right? And basically the color represents each individual year. So let me just put again, these two are the wetlands, and then these two are the forests. These are the temperate sites. And if we kind of go through, kind of give a picture of what this looks like throughout 1 year. So if we look at Sylvania here, at January 1st, we kind of start off, and we go above 0 for most of the lines, which indicates a carbon source. And then as you get into the growing season, you have leaf out, and then that causes photosynthesis to happen and carbon uptake, right? So then your net ecosystem exchange becomes negative, and therefore you have a carbon sink at that point. And these last kind of not dots, but the last day of the year kind of shows how much carbon that particular ecosystem accumulated in that year. So now we can see this a little bit clearer, right? Where you have much more variation at the forest sites relative to the much more constrained wetland site here. Of course, all across Creek did not have much data, but just comparing it to the wetland site here, you can see that these two forests are highly variable. Now, you can also, in addition to Eddy, look at GPP, right? That carbon uptake term. So here is GPP, and I've added the boreal sites as well. Here is kind of this is a key of how you should read this. So we got the equation right here. The site ID colors. So each site is labeled with a different color. Now that determines whether it's, that signifies whether it's a deciduous broadleaf forest or mixed forest, and then wetland or evergreen needleleaf forest. And then also the unmolded and molded texts represent temperate and boreal regions, respectively. So here you can see GPP as a function of day of year, grams of carbon per meter squared. You can see that at the forest sites, and this doesn't seem to be dependent on the, and I should say the deciduous broadleaf forest sites or the mixed forest sites, because the evergreen needleleaf forest kind of does its own thing. But if we look at just those deciduous broadleaf forests and the wetlands, we can see much higher GPP at the forest sites relative to the wetland sites. And it seems like it's much more constrained at the wetland sites relative to forest sites. And this does not seem to be a kind of a function of the region we're looking at, because we see kind of similar magnitudes of fluxes between the temperate and boreal regions. So GPP, we can also, in addition to GPP, we can also look at our eco. And so this is how much the ecosystem is respiring, right? How much it's giving off carbon. So here, interestingly, with the exception of Sylvania, which is the old growth mixed forest, we see relatively similar magnitudes between the respiring carbon fluxes. And this goes to show that there is a lot of very similarities in these carbon fluxes when you look at the R-eco term versus the GPP term. And it suggests that over long time scales you have similar fluxes when it comes to kind of giving off that carbon into the atmosphere for each of these ecosystems. So it's relatively, we can say that there's a high, there's not much of an ecosystem type or regional dependence in terms of these fluxes, at least for these things. So now what we can do is look at NEE, right? Applying this equation, taking R-eco and subtracting GPP from it. So I already showed you the first row a few slides ago. There's the temperate sites, but now adding the boreal sites to the mix, we notice that there is high variability, right, in these forest sites, the boreal site, relative to the wetland sites. And so this kind of suggests potentially that there's not much of a ecosystem or ecosystem regional dependence, but there's an ecosystem type dependence that occurs when you're looking at these carbon fluxes on a long time scale. Of course, you have your evergreen needleleaf forest kind of doing its own thing, and yeah, you see this constrained wetland flux, and it's kind of similar to the constrained temperate wetland, and then it's constrained boreal wetland, and then the other sites as well. The forest sites are showing high variability, as I mentioned. So we can also take a look at something else. In addition to this, I also kind of created a violin plot that showed the different NEE zero crossing days. And what NEE zero crossing day is kind of, what you think it is. It's basically when NEE crossed that 0 point. So when NEE went from positive to negative, indicating when the ecosystem went from carbon source to carbon sink. So the day of the year that that happened is on the x-axis here. You have the sites in the same legend on the y-axis, and indicates how many years of data we had available for that particular site. So again, and the violin plots themselves, blue is the wetland, and then the green are the forests. And you can see much larger spread, right? You have these forests, especially the temperate forests, taking up carbon as soon as day 120 and as late as day 220. Whereas the wetlands, especially Lost Creek, has this confined 160 to about 190 day of year carbon flux change. So this also indicates kind of a different, a way of kind of measuring how variable the forests are relative to the wetlands. And it seems to kind of hold true that this seems to be an ecosystem type phenomena and not dependent really on the region that we're looking at. Okay, so now that we've looked at the carbon fluxes themselves, now we can dive into the drivers. So what is driving these carbon fluxes? We looked at air temperature, photosynthetic photon flux density, which is basically the radiation, you can think of it as radiation, latent heating, and precipitation, and then stream flow or discharge. So I first looked at precipitation because precipitation is a very sporadic variable, right? It's not very continuous. I conducted a very basic linear regression analysis just to show kind of if there's a relationship between these carbon components and the different drivers. So I did it against GPP and NEE. There was not much of a statistical significance in that for those two variables, but when plotting it against, so when plotting our ecosystem respiration as a function of precipitation, there looks to be a correlation that is very weak, but statistically significant. All of these p-values were less than 0.05, and yeah, whereas for the other ones, they were not significant at all. So there is something going on here, and this doesn't say that precipitation itself is causing this. There's definitely a middleman right here, such as soil moisture, that's causing this to happen. Right? You have the rewetting and wetting of soil that has been linked to carbon emissions from ecosystems. And yeah, each of these R values are between about 1.15 and about 0.25. So, and it doesn't seem to be differing in terms of the ecosystem type. I forgot to mention that I've also, as you can see, I've partitioned these into daytime and nighttime based on these hours of the day, just to see if radiation was kind of a confounding variable in this. And again, yeah, I forgot to put this, but this is the legend that you've seen in the previous slides as well. So, other than precipitation, all those other variables had a relatively more continuous data. So I wanted to use a much more sophisticated method to kind of quantify their relationships between these drivers, or the carbon fluxes. So I resorted to information theory. Information theory was first proposed by Shannon et al. 1948. And it basically has this thing that we can use called mutual information within it that quantifies the amount of information gained from one variable by examining the other variable. And it's a measure of mutual dependence between variable x and y. So this renders it very useful for comparing different things, such as what I'm about to do, the carbon flux and driver analysis. And this has been done before for methane fluxes and biophysical variables by Knox et al. 2020, and basically now applying this to the carbon dioxide fluxes. So how does this work? We need a game plan, right? This is a very complicated form of analysis. So to apply information theory, we have to define our x and y. X we can set as NE, or y, excuse me, y we can set as NE, and then x is your carbon flux components and drivers. Carbon flux components are GPP and our eco, as I mentioned before, and then you have your drivers being PPFD, photosynthetic photon flux density, so radiation, air temperature, radiant heating, and then discharge. So in addition to this, if you recall the research questions that I wanted to kind of answer, is that I wanted to take this and look at it on different time scales as well. So working with this half-hourly data, I need to figure out a way to get this into different time scales. And to do this, I basically took a wavelet decomposition approach, particular a wavelet transformation. So this was, I basically used the Sturdivant et al. 2016 approach to get this half-hourly scale data onto kind of these different time scales, as you can see here. And I just want to mention that the maximal overlap discrete wavelet transform, that's what that stands for, that function in MATLAB I also used to facilitate the process as well. So using this, I could get from the half-hourly data to have the raw data, could go all the way to that yearly scale, and then everything in between as well. So just to give a sense of how this works, I know this is very abstract, just to show kind of the different stages of this. So you start with your half-hourly data, it kind of looks like this, a lot of wiggles, everything. So this is the Lost Creek NED data, the temperate wetland in northern Wisconsin. And as you apply these coefficients that are provided by that MATLAB code, or MATLAB function, you go to hourly scales, then dial scales, and now multi-day scales, and I can kind of see the different troughs and peaks, right? Seasonal scales, this becomes much more apparent now. And then lastly, yearly scales, which gives you this profile right here. And this was applied to all of the carbon fluxes, all the carbon flux components, and then also all of the carbon drivers as well. So once you do all that, what you get is the following. So this is a lot of information. The colors are not really appearing that well, but I think you'll get the gist of it that basically what you're seeing here is a heat map that shows on the y-axis the ecosystem site, and then I think the legend is the same basically as before. The ones with dots in them have no data available, and yeah, the x-axis is your carbon flux component or your carbon driver variable. And then the shading, so the higher shading means that particular carbon flux component or carbon driver was a large predictor of NEP, and then a smaller shade or less of a shading of red means that it was less of a predictor of NEP. So what we're looking at here is hourly and dial scales, and I think this doesn't have a large enough color palette, but these are supposed to show hues of red. They look white here, don't they? Yeah. So on hourly and dial scales, I think just the main point here is to see that, and I think this is because the GPP here didn't have data, so maybe that's why our eco is kind of more prominent there. But at each of these sites, on short time scales such as hourly and dial, there is a much larger dependency of NEP on this GPP. So the GPP component is kind of dominating in terms of that interannual variability, or on these time scales. Excuse me. And we can also look at this on multi-day and seasonal, right? And now you see that the GPP and our eco are relatively balanced in terms of their prediction of NEP. So multi-day time scales have a kind of a balanced prediction between GPP and our eco. And then the drivers don't seem to be kind of influenced one way or another. The magnitudes are approximately the same, the prediction is approximately the same between both ecosystem type and also the region of the ecosystem. But now going into seasonal time scales is interesting because we see that there is much larger shading at the boreal sites. So recalling that these bolded sites are the boreal sites, you can see that the ecosystem drivers are relatively more predicting NEE much more at the boreal sites relative to the temperate sites here, as indicated by the much more red shadings relative to the lesser red shadings above. And this kind of translates to yearly scales as well, where you have this darker shading relatively at the boreal sites relative to the more lighter reds at the temperate sites here. So that's interesting. So we're seeing a much more ecosystem region dependence on these biophysical variables, on predicting NEE, on longer time scales, so those seasonal and yearly scales. And the time series itself, as we saw previously, the carbon fluxes themselves are very ecosystem type dependent, it seems like. That's interesting. And then, so now going and looking at the last question here, just to put this in the context of NCS, just some recommendations here, so recalling that NEE is equal to R equal minus GPP again. And then the goal of this, right, is to maximize GPP and reduce R eco, right? You want much more carbon input on long time scales relative to that carbon source term. So one way to do this is to take part in reforestation and afforestation efforts, right? As the analysis showed on short time scales, there's much more dependency of GPP, or much more dependency of NEE on, or GPP is a better predictor of NEE on short time scales. So this will kind of give that boost that's needed on short time scales for that carbon flux, or for that ecosystem to become a carbon sink. We saw that wetlands are less variable, and that kind of renders them a much more reliable ecosystem. So I think prioritizing wetlands more so over forests would provide, a better carbon sink for the long term relative to kind of that forest unpredictable carbon flux that we see on a long time scale. And then this just goes to show that that the ecosystem scale measurements that we've done here play a large part in informing these NCS mitigation strategies, right? So a paper by Heaves et al. 2021 showed that these Eddy covariance flux towers provide a large, play a very important role in providing these measurements. Whereas, we see a lot of regional studies and global studies, but it's also important to include these ecosystem scale studies as well. I think this study is kind of interesting with that. So just some concluding remarks just to summarize all this. So that was a lot of information. So I'll get this grid up. Okay, so first we looked at time series of carbon fluxes, right? And the time series showed us that forest carbon dynamics, for these sites at least, are highly variable, and they have high rates of uptake from year to year. Whereas wetlands, this is less variable with relatively low rates of uptake. And then linear regression showed us that our eco and precipitation are positively weakly correlated, and this is most likely due to soil moisture and the dynamics with that. And then lastly, mutual information showed that GPP is a dominant predictor of NEE on short time scales, so hourly and dial scales. GPP and our eco are kind of relatively similar predictors of NEE on longer time scales like multi-day, seasonal, and yearly. And then lastly, that the boreal drivers are more of an NEE predictor than temperate drivers on these long time scales such as seasonal and yearly scales. And then just to go into some of the future work. So I want to extend this analysis to the tropics because the tropics are a very hot area of research right now because they, nobody really knows in the context of climate change of whether these ecosystems are going to become carbon sources or sinks. And there's a lot of deforestation that's happening that's kind of contributing to the exacerbation of that effect. Particularly, I want to look at peatlands. So peatlands are, in the tropics in particular, are interesting because even though they don't cover much of the land area, they contribute disproportionately to the carbon stock in that region. So, if these ecosystems if this peat was to all of a sudden in the presence of climate change or any other external factor become a carbon source, so all of a sudden releasing all that carbon that's been accumulated for thousands of years, then that would be a very, very horrible situation. And that's why they're kind of paramount importance right now in terms of research. And then lastly, of course, I think all of this is to constrain these land carbon cycle models, right, informing making these observations so we can have more input and make these land carbon cycle models a little bit more reliable in terms of projections and also decrease the uncertainty as well. Okay, so I think that's all I've got. Just a few acknowledgements I want to make. I want to, first and foremost, thank my advisor, Ankur Desai. Thank you so much for all your mentorship over the 3 years. It's been a joy to work with you. And then, of course, my committee members, Paul Stoy and Min Chen. I want to thank them for providing very helpful feedback on my manuscript. All the graduate students, of course, this is not an all-exhaustive list. Thank you for all your company, and just it's a great time. I'd like to talk with y'all and hang out with y'all. And then my family as well, and my dad, and my mom, and my sister. I want to thank them for being patient with me throughout the process and kind of supporting me throughout this journey as well. So that is it. This is my email and then my Twitter handle. But yeah, if you have any questions, I'd be happy to answer. Thank you.
We have time for a few questions.
Yeah, that mutual information technique was really interesting. I was wondering why you chose to use the RECO and the gross primary production as predictors of NEE, because they're right in the equation. So to me, it seems like of course they would be predictors because that's how you calculate the third one. And I wonder if that is kind of diluting some of the other signals.
Right. So I think my best response, let me go back here. My response to that would be that we want to determine the amount of influence that these two terms have on that. You know what I mean? To see if whether GPP has a higher influence on NEE relative to RECO. And you're right. They're within the equation. It's literally NEE is literally composed of that, right? But yeah, we just wanted to see whether the partitioning of that. So since NEE is partitioned into two different components, we just wanted to see if there was more of a dependence on NEE on one variable relative to the other on different time scales. This kind of the idea.
So I think it would be really interesting to see if you just use those two components and then just did the atmospheric variables to see what else shows up, especially.
Oh, yeah.
But I don't know how the analysis technique works, so I don't know how much that would change things. But
yeah, I don't know either. Yeah, that'll be interesting.
Really interesting.
Yeah.
Do you see signals of climate change in these variables? Do you think there's a trend over the years of whether these things are changing?
That's a good question. Yeah. The only climate change signal potentially that I saw, I have to press it a lot, is in the time series. So I just get into that. Particularly in Lost Creek, right here. So as you can see, the different years are the rainbow, right? Where you have the reds and oranges in earlier years, and then the blues and violets in later years. What you can see here is, a lot more blues and reds on the bottom relative to the reds and oranges on the top. So this potentially might be a CO2 fertilization effect happening, I don't know. But that's the only thing that I noticed, because this is basically suggesting that as you're going further and further in time, that you're getting much more of a carbon sink, right? And this particular site. And of course, I'm not sure about all across because there's not much data. But yeah, that's like the only place where I would say that potentially, like I have to look into it. That's where I kind of see something. Yeah, James?
What's your interpretation for the yearly mutual information?
Yeah,
It
here.
looked like the evergreen had a higher mutual score. What's your interpretation of that? Is that just evergreens are more consistent or constant over yearly scales?
Yeah, so right here, you're talking about the,
SEC,
yeah, SEC.
it's darker across all.
It is, it's darker across all of them. Yep, yep. Yeah, so SEC, if I remember correctly, didn't have much data available. But you're right, so I'm sure there's like has something to do with that, where it's like on yearly scales, you have much more dependency on this. It might be also due to, them not shedding their leaves,
Their
right?
evergreens.
Yeah, something like that. I would have to look into it more. But that's interesting where it's kind of constant throughout. But yeah, I have to look into that more. But I would guess it would have to be due to them not shedding leaves annually, whereas all of these other sites are shedding leaves. Yeah.
I'm curious if you have any hypotheses or ideas for how analysis, so if you apply this to the tropics, like how the tropics, like the results from the tropics might be different in these sites in like the mid-latitudes and high-latitudes.
Yeah, right. So the question is like how this would affect, or how these results would differ, like in the
Yeah,
tropics.
I'm just curious
Yeah.
if you like thought about that at all.
Yeah.
Like Australia.
Not yet,
You might
yeah.
anticipate. Okay.
Yeah, no, that's a good question, but that's like literally, what I want to do.
Yeah.
And there have been signals that, there's been a lot of papers that have looked at
Mhm.
higher temperatures in the tropics, right?
Okay, yeah.
So, I don't know, sometimes higher temperatures cause larger respiration rates, sometimes they cause larger uptake rates. So I'm not sure what I would see. Yeah. I'll have to look into
It'd be
it.
interesting.
Yeah, that would be interesting. It's a good idea. Yeah.
So I think maybe a general conclusion from your work is that you can kind of divide the world into organisms that kind of live fast and recklessly, and those that kind of are slow, steady, but very cautious, right? And it's almost like if you're trying to enhance or trying to lock carbon into a system, you want something that kind of hits a sweet spot between the two. And I wonder if the same applies for climate too, right? Because you're looking at NEE variability, but there's also climatic situations where you're more likely to be facing extremes, and I don't know if that kind of an evolutionary model could apply to some ways to because your work suggests wetlands do their own thing wherever they are, but my first instinct would be that sites with high climate variability kind of are going to be ones that are going to be more opportunistic because they have a much greater chance of mortality or low years or bad years or something like that. So I'm just kind of curious what your thought is on how to reconcile that.
Sure. So you're suggesting kind of the larger internet variability to be a little bit more reliable in terms of the long-term sequestration?
Well, I don't know if it's more reliable, but I think it's an evolutionary strategy, right, that's related to climate variability. You suggest that wetlands are just persistently cautious ecosystems, which is a really interesting. I don't know how that evolved, right? Even though you have large differences in climate variability. I'm just curious what you think about wetlands.
Yeah. So I think I don't know, when I first saw this, I guess going back to the time series here. So in my mind, the constrainment of the wetland sites tells me that there is a greater potential for them to have lower risk of sequestration reversal, right? Because they have, you don't really know, and kind of the next analysis right here shows that you don't really know what these forests are doing from year to year. And therefore, if you kind of take the safe way out, I think that's why kind of the wetlands are orchestrated that way. Does that make sense? Or did that answer?
Yeah.
But,
It's a big question right now because so much money is going into forest restoration, and yet you have all these disturbances, fires, and other things. Meanwhile, you have these relatively left alone wetlands that can maybe even do more.
right. And the forests are, I guess I should mention that the forests are more ubiquitous, right, relative to wetlands. So I don't know how that would play a role, right? If you restore more forests, will that change the way we think about mitigation strategies, or yeah, something like that. So,
That's time, so we should probably quit. But let's give Nikaan another hand.